Hi everyone, today we're going to spin around the y-axis to find our volumes using rotation, okay? So let's go ahead and look at a easy start. This is a basic problem. Let's look at x is equal to, here we go, x is equal to negative y squared plus 4, and we're going to be bounded by x is equal to 0, okay? Now, looking at this graph, this is a sideways parabola. Whenever you see a y squared, that's going to be a sideways parabola. Negative, so just to FYI again, just in your brain, we have positives and negatives, right? Positives and negatives. So if we're doing a parabola going this way or this way, if you see a negative y squared, of course we're going to go in this general direction, going down. If I plug in y is 0, if I plug y is 0, x is now 4. Just a couple numbers that we can pay attention to here. 4 easy values for that we can derive. So we have a parabola going this way, and we are going to spin around the y-axis. So here's our y-axis spinning it this way. So we also said we're going to be bounded also by x is equal to 0, and x is 0 right here. Let me go ahead and just draw a line here. That's our x is 0, and we're spinning around our y-axis here. So that leaves us only a small bit of graph to worry about, and that's our graph going this way. Now, we always draw our rotations, our little disk in the direction of the rotation. So if I'm rotating in this direction, I'm going to be drawing a disk going kind of like this way. Oh, that looks a little ugly. Let me erase all this stuff. Okay, we're going to go in this direction. Let me draw my mirror image. A mirror image would be something like this on this side. And since we are stopping at the x-axis, we're going to end up with this little like dome cake here. Okay. Hopefully you guys can see that 3D image going on. And that's the shape we're getting. You can see, since we're spinning around the y-axis, is this going to be a disc or washer? Ask yourself that question: is this a disc or washer? Since this is the start, this is probably going to be a disc, right? It's a solid shape. So let's take a look at just the cross section here. To find the area of this disc, we're looking for the radius. Now, if you look at the radius here, it's not like our typical problem when we were going, the radius is going this way, where that's just f of x. That was our radius when we rotated this way. That was our rotating around x, right? Axis. That's this guy here. We're rotating around the y-axis, so my radius now going this way. So I want you guys to look at this instead. I'm going to go ahead and erase all this extra fluff here. And we're looking for the radius, and the big deal is this value from here to here. How do I get from here to here? So for us, we mentioned before, it's right minus left. Right minus left, and that'll give us our radius. We're still working with circles, so we still use the equation integral of pi r squared. And here is our problem. We used to use dx going this way as integral of pi r squared dx because we want a small sliver of dx. In this case, we want a small sliver of dy. Okay, so that's our setup. We switch our axis. That means we're going to switch from dx to dy now. We want to figure out what is the distance from here to here. And folks, let me ask you, is this distance an x or a y value? Is this distance here an x or a y value? That's an x value, and that's where we're going to use this problem here. Right is negative y squared plus 4. My left is going to be x is equal to 0. And we're going to subtract those from each other. The r value is negative y squared plus 4 minus 0. We don't need to write the minus 0 here, but this is totally optional because this is axis of rotation is around 0. So our problem is going to go pi r squared, just like what we did before, dy. Now our boundary is in this y direction, right? See how this is in the y direction? So we're going to go in this direction. So we're going to start from our lowest, meaning 0. And where does it intersect the y-axis? I don't know. Negative y squared plus 4. When does this equal to 0, right? Because that's my x value. When does this equal to 0? That's at negative y squared equals to negative 4. Y squared is equal to 4. Y is equal to plus and minus. The square root of 4 is 2. So for sure, negative 2 is not what we're looking at. We're looking at positive 2 on top, so 0 to 2. So the reason why this is slightly different is because we had to switch around our variables. We had to switch around the way we look at it. But it still practically follows all the same steps that we did for rotating around the x-axis. Okay, let's look at another problem here. So I forgot the squared here. Remember, this is just a pi r squared, which is a area of the base times a little bit of height, I guess you could call that, or width, and that's our dy. So we're still adding up circles, but instead of stacking them this way, we're stacking them this way, going up. Okay, let's look at another problem. Let's say x is equal to negative y squared plus 1, and we're going to be trapped between x is equal to 0, y is equal to 0, and y is equal to 1. Okay, so we got a couple of boundaries here. And again, we're going to rotate around the y-axis. Alright, so if I want to draw a basic picture of this, a couple things you can plug in that I think aren't very hard is first that we know this is a parabola going left. And if I plug in y is 0, x is equal to 1 now. Right? That's our point on the graph. Parabola facing downward, sure, we can go down this way, right? Automatically we can be thinking about this. They gave us a couple of boundaries though. They wanted x to be 0, so we're stuck on top of the graph. They wanted us to be blocked by y is 0, and we're blocked by x is 0, right? Y is 0, and y is 1. So our graph is actually going to be stuck right in the corner here. So that's the graph they want us to rotate. Rotate around the y-axis, going this way. So it looks like, again, we're going to end up with this bun cake thing. Now, what is the shape that we're trying to define the area of? This is, again, a circle. Right, that's a circle. We follow our equation, pi r squared. Integral of pi r squared. We're going to be going in our y direction, so we're going to say dy. Now, your goal now is to find what is that radius equation. What is our r? And the r is, if you just draw a line using a pencil, it's from the function on the right minus our axis for rotation on the left. So the r is negative y squared plus 1 minus 0, or r is negative y squared plus 1. That is the radius of our graph. Okay. So we just plug it in. The integral of, I'm going to throw pi on the outside, negative y squared plus 1 squared dy. Now we got to make sure we have our limits correct, going from where to where. Since this is starting at the floor, they told us to start off at y is equal to 0, and they want us to go all the way up to 1 here, and y is equal to 1. So this was predetermined for us. Not super hard at all. Unfortunately, we have to be able to spin our brains around. Now, these problems here are set up for you. They're set up as x equals 2. Why are they set up as x equals 2? Let me draw this as a bigger version here, please. looking at a graph being rotated in this direction, we end up with a rotation going this way, right? We're rotating around this axis. Our radius is given by this value. Now, is this an x or y value? This is an x value, isn't it? And that's why our radius is being plugged in as an x value. What if you're given a y value? What if we are given this problem just like what we normally would see? What if I gave you guys a problem that looked like if I gave you a problem that looked like y is equal to x squared. We're going to be trapped between y is equal to 1, x is equal to 0, and x is equal to 1. So we've got some boundaries on this graph. Basic parabola. We've seen this parabola before. So let's go ahead and redo this problem. I want to rotate this around. Rotate around the y-axis. Okay, here we go. Let's draw this parabola like we normally would. That's a 0, 0, 1 over 1 space up. And then we can go 2 spaces, 1, 2, 3, 4 up if you want. And draw our parabola going up. But we don't need all this parabola, okay? We don't need all this parabola. Because we are bounded by y is 1, x is 0, and x is 1. So we're going to be stuck in this corner here. And here's the idea. They're telling you what part am I bounding, okay? I'm bounding by up here, down here, and we're stopping here. And the graph itself, we are being bounded in this little corner here. That's our graph we're worried about. Because the alternative is, are we talking about this guy down here? Which one are we talking about? Are we talking about the lower part or the upper part? And these bounds kind of focus you in this is the corner that you're stuck in. These are your 4 walls of the room. Let's take a look at those four walls again. The question is, are we going to be bounded in this corner up here? Or this corner down here? If you're colorblind, I'm sorry. Which of these am I going to be bounded by? Because sure, I could spin it this way, and you would end up with a shape that looks like this little bowl here, right? That could be our shape. Or if we spun it in the red, you would end up with a shape that looks like right. We would end up with 2 different shapes. Totally 2 different shapes. Depends how we spin this and which section we're talking about. So let me go ahead and again re-illustrate these boundaries. Y is equal to 1. So that's the top graph. X squared, that's this graph, right? So far, seems like we're going to be trapped there. X is 0. See how we're kind of trapped in this corner? And then y is 1. Right? Just to stop us there. Now, as you can see, we don't have no boundary here. This could go on forever. Oh, never mind. Yeah, that's right. Okay, so we're stuck in that corner. So it's important to figure out which part are we trying to rotate. Okay, so the next issue again, let's go ahead and write our equation. We know we're going to be rotating in the y-axis, so this is going to be the integral pi r squared dy. Right, so I'm going to just draw one little circle here. So yes, I'm going to go in this direction. So if I'm drawing it in this direction, I need to find the radius, and that radius is an x value. Unfortunately, they did not give us the correct equation here. So we are going to now convert this y equation into an x equation. how can I get y to x? Let's go ahead and solve it. Y is equal to x squared. Solving for x, we take a square root of both sides, plus and minus. Now let's write it out. X equals to plus and minus square root of y. Now do we want both these y's? No, in this case we only want the positive version. We only want the positive version. So x is equal to the square root of y. Now, just if you guys didn't know this square root of y graph, let's go ahead and plug in some numbers. If I plug in 0, if y is 0, x is 0. If y is 1, x is positive 1. If y is 4, x is positive 2. So we have this parabola on the right side. If x is negative y, square root of y, the other graph, let's plug in numbers. If y is 0, x is 0, great. If y is 1, x is negative 1, because square root of negative square root of 1 is negative 1. If y is 4, that gives us x is negative 2. So please take a look. The idea here is that we have to write a plus and minus version because since we switch axes, this doesn't follow. Remember how functions, the vertical line test is a function? The idea is this is a function going the other direction. So we had to write the plus and minus version. So we're using this guy here. Okay, so we know what the value of the x is, and we just do right minus left. In this case, our right equation is the square root of y. Our left equation is 0, right? We're going to be 0 here. So the radius is just square root of y. Integral pi r squared y square root of y squared dy. And this is one thing you want to make sure that these variables are exactly the same, right? If not, you pick the wrong variable. We're going to go from 0, and we're going to crawl ourselves up to our boundary y is equal to 1. So in this case, we're going to go 0 to 1. So this illustration is, what if they give me a y equals equation when I'm spinning in the wrong direction on the wrong axis? That means you're going to have to algebra your way through solving for x. Algebra your way through solving for x. And then it goes back to our original problems that we've been working with. Okay, let's see. Let's go ahead and do a problem where we're shifting axes. So here's a problem. X equals to the square root of y plus 1. Okay, so do we know what that looks like? Square root of y. We literally just did it, right? A square root of y looks like a square root problem, but going in the wrong direction. Now, just sometimes these problems are pretty easy to set up because just plug in numbers. So let's plug in easy numbers. If y was 0, isn't y 0 right here? That's y 0. If y is 0, plug it in. We have x is 1. If y is 0, x is 1. Let me create a table for you then. If y is 0, x is 1. Pick easy square roots that you know. The square root of 1, right? Square root of 1 is 1. If y is 1, that means we end up plugging square root of 1 plus 1. That's going to be our x is 2. Easy graph values. If y is 1, x is 2. If y is 4, the reason why I choose 4, because I can take the square root of 4. Square root of 4 plus 1 is now 5. Oh, not 5, 3. Right. So if x is 3, y is 4. You guys can see this is a parabola going to the right. If I want to say, what if y was, can we do negative values here? Would -1 work? Would -2 work? Would -3? No, because we would take the square root of a negative. And then that's why this is only a one-sided parabola here.
Would you be able to like convert it into a y equals equation, or is that
You,
just not worth it?
well, you can. Like, since you're just learning, since you're practicing, you might be able to see the pattern. If I rewrite this as a y equals problem, this is x minus 1 equals to y, square root of y. Y is equal to x minus 1 squared. And this is just a parabola with a vertex of 1, 0. 1, 0, parabola shifted over just to the right. But if we switch it over, we don't see that this graph doesn't exist on the left side.
Oh, I see.
And that's our dilemma. Like, this graph actually doesn't exist here for the problem that they gave us. Now let's go ahead and give ourselves some constraints. Let's say, throw in some constraints here. Let's add x is equal to 1, that's a constraint. Y is equal to 4, that's a constraint. And then we're going to access a rotation. We're going to rotate x is equal to 1. Okay, so let's throw in some constraints. So we're going to stop it as x equals to 1. Here's x is 1. Here's my x is 1. We're going to say y is 4. Y is 4 is way up here. And we're bounded by the graph. So you can see that we're rotating this portion of the graph. If they change the constraints and they, for instance, try to show you that the constraints will be over here, we would be rotating this portion of the graph. So the constraints help us figure out what part of the graph we're trying to rotate. Okay, then we're going to rotate this around the x is equal to 1. Here's x is equal to 1. So we're going to rotate around this way. Now, if you want to, you can, again, just draw one. You can draw the reflection if you want, if you think that's helpful for you. Great. You can draw one example of a disk. Right? That's our disk. And the biggest deal, I think, that what we need is we need to figure out what my radius is. And that's really the key element to this. What is the radius? And that's going to be our outer radius minus our axis of rotation. In this version, it's going to be the square root of y plus 1 minus 1. And that's our radius. Everyone see that that's my radius? These are just values, and we're subtracting these values. So let's set up integral. We'll figure out the integral in a little bit. Pi, our radius squared, is y plus 1. Actually, let's write over here. R is equal to square root of y plus 1 minus 1. It nicely simplifies out. R is equal to square root of y. And the dy. We want to make sure we have our a to b value. We're crawling this way, right? Because this is dy. So make sure you know which way you're crawling. So we're crawling from 0 all the way up to our value 4. Right? The setups can be easy, but they can also be super annoying. Now, let's take this same problem, since we already have it drawn out, and let's give ourselves another problem very similar to this. But I'm going to switch the axis of rotation. So I'm going to take this problem here. I'm going to switch the axis. And we'll see how this problem changes. The axis to x equals to -1. Okay, so we're going to take this axis and we're shifted over. We're still going to be bounded by 4 on top. We're still going to be bounded by, actually, we're not going to be bounded by y, so x at 1 anymore. And but we're going to give ourselves a bound at x equals to 0. So here's our boundaries. Our boundaries are y is equal to 4 and y is equal to 0. Okay. So let's draw this one slightly different. So we said before we are graphing to this parabola looking like this. Okay. except -1 now is my axis of rotation. So we end up with this huge block that I'm going to spin around, right? So we end up copying 1, 2, 1, 2, 1, 2. Here's my little fat salad bowl going on. Right, so now we're a big salad bowl going on. Because I just switched my axis of rotation. Right, we moved it over. So what is the radius of this little monstrosity? We'll just draw a line. I find drawing a line from your radius to the axis of rotation is super helpful. This equation we said was square root of y plus 1. This equation here is -1. So our new radius is square root of y plus 1 minus 1. And this becomes square root of y plus 2. And this kind of makes sense. My radius is just 2 spaces. Look, take a look. It's 2 spaces bigger than what it was before. Okay, 2 spaces bigger. Great, awesome, fabulous. So integral from 0 to 4, like we said before, pi r squared square root of y plus 2 dy. Nothing's much changed. The concept is still the same. Okay, let's use the same idea now, and let's make this into a washer. Now what if I kept these constraints? What if I said x is equal to the square root of y plus 1, and the graph is bounded by x equals to 1, y is equal to 4, and y is equal to, yeah, I think that's all we need, right? Yep, those are all the constraints we need. And we're going to rotate around x equals to -1. So we're going to take our graph that we drew. We've been using this graph for a couple times already. Here is my 1. My parabola goes up. Come on, parabola. Okay, that's my parabola. We're going to bound ourselves at 1, bound ourselves at 4. So we're going to only rotate this object around. I want to do my mirror reflection on the other side. Here's my -1. Give myself 2 spaces. I'm going to draw my little reflection here. And hopefully you see there's a lot of kind of dots here, but we end up with 2 okay. See that big hole in the middle? Now how do we say we deal with washers? And the easy way is you don't. You just deal with 2 separate objects. Now we have a quick formula that we can get to, so let's do the slow formula first, then we'll do the quick formula, okay? The slow formula is to actually write out 2 different integrals and we subtract those integrals from each other. 0 to 4, 0 to 4, pi, pi, and we're just going to do r squared dy and then r squared dy. Okay, remind you this is square root of y plus 1 and our axis of rotation is -1. So let's do 2 different colors. Let's do this is my large R and this is my little r. Okay, and that's going to remind us that's going to be 1 here. Okay, that's going to be 1. So what is the large radius? The large radius is r is square root of y plus 1 minus -1. That is my large radius. That's the whole object as a whole. What's the small radius that we're trying to cut out? That r value is 1 minus -1. Okay, so my r value here is going to be 2. My r value here on my left is going to be the square root of y plus 2, right? Negative 1 is plus 2. And that's what we write into our radiuses. Now, what's a fast way of writing this? Our formula for the fast way of writing this is pi integral of capital R squared minus little r squared dy. That is our fast way of writing washers, which is exactly the same thing here. They both have a pi, and they both have an integral, and we're just minusing the r squares. So you can jump by saying, hey, they're both going from 0 to 4. Right? This is one continuous object. The outer radius, we simplify to be just square root of y plus 2 squared minus, what's the inner radius? We said that was just 2. And don't forget this extra parentheses here, which you need. That's a washer. Okay. So the setup for either rotating around the x-axis or y-axis is actually the same setup, right? The steps for us to find the radius are exactly the same. The only difference is that we are just now in a different orientation. And also the big deal is that if they give me the wrong function, either x or y, we have to convert it to whichever radius I need. So let me just refresh this real quick and just say which radius do I need. If I give you a graph, and let's say the graph is spinning in this direction. We're spinning in this direction. Okay. What is the radius? The radius is a y value. Okay, see that's a y value? So we're going to be subtracting y's from y's. So I need this to be a y equation. But if I'm rotating the same equation, that looks a little bit weird. Oh well. But you guys get it, right? So if I'm rotating in this other direction, take a look at your r. Your r value here is an x value. So we need to be subtracting x's from x's, because that's how we end up with our radius. So this equation here has to be a x equals 2 equation. X value. Okay, that's super important for us to know. So they give you the wrong value, we're kind of screwed. So also another thing I want to say, hey, aren't we making our circles, aren't these little slices of dx? So this integral will be the pi r squared in their dx fashion, because these are slices of x. Us going this way, we're stacking up Oreos, right? It looks like we're stacking up a bunch of Oreos, I guess. This is the pi integral r squared. Yes, it's still radius, but we're taking slices of dy. So when they give you a problem, let's do one more. And they say y is equal to the square root of x minus 3. Let's give us a bound. Y is equal to 2, x is equal to 3. And they want you to spin around the axis of rotation, x is equal to 2. All right, sure, let's draw this out. What does this graph look like? To help you out with square root graphs, if you don't know how to do them, think about the square roots that we know. We know the square root of 0, the square root of 1, the square root of 4, the square root of 9. Only use these numbers. Okay? How can I make x become 0? How can I make x minus 3 become 0? If x was 3. 1, 2, 3. If x was 3, 3 minus 3 is 0, y is 0. Okay, let me give you a table real quick in case you guys need this. X and y, right? If x was 3, y is 0. Okay, square root of 0. I should write that. Easy peasy. If x was 4, isn't 4 minus 3 1? Hey, square root of 1. We know what square root of 1 is. When x is 4, y is 1. I don't know if I plug in x is 5, 5 minus 1 is 5 minus 3 is 2. I don't know what the square root of 2 is. Screw it. Let's find something I do know the square root of. I know the square root of 4. So if this was 7, 7 minus 3 is 4. Hey, square root of 4 is 2. At 7, which I'm not going to draw, we know it's going to be way over here. That is your graph. Let's look at the boundaries that they told us. They told us y is equal to 2. Okay, y is equal to 2. Oh, here, this is 2, right? So we know we're going to get to 7. Oops. I should have did a better graph here. 3, 4. 4 is 1 and then 7. 5, 6, 7. Here's 7 over here. So we're going to stop way up here. That's my top bound. X is 3. Here's my next bound. Do you see us trapping the graph? This is the portion of the graph we care about. We care about that portion of the graph. They want us to rotate it around x equals to 2. Fine. Here's x equal to 2. Right here. Unfortunately, this looks like a washer to me, right? We're going to be rotating in this direction. So let's break out our washer rule real quick. Pi integral r squared minus r squared. And since we're spinning around the y-axis, this is going to be a dy problem. So give yourself some clues, some setups, so you don't mess up. Okay, so I'm going to go ahead and draw an image of it. Now let me tell you this, if we're taking a test and there's not enough time, unless if you really need it badly, do not draw this graph. It's just a waste of a bunch of time. But if you need the imagery, fine. Right, we have a washer in the middle, and this is going to be this huge like disc shape going on here like that. Okay, we have this shape going on. You guys see this shape? Oh, that's not going. Okay, and then we have like a hole in the middle, right? Okay, you guys see the shape? All right, so now that's too much. I'm going to erase all this stuff. Because we only need radius. Looking at the shape is great, but we only need the radius. So let's go ahead and find the radius. Here we go. Here's my axis of rotation right here, right? We said that's my axis of rotation. What's my outer radius? And what's my inner radius? Now the problem is, this equation is written as y is equal to the square root of x minus 3, right? But remember I told you guys about the radius? We need an x value for the radius. And that's not an x value. We want to go right minus left. So let's go ahead and convert this. Y equals to square root of x minus 3. Square both sides. Y squared is equal to x minus 3. Y squared plus 3 is equal to x. Now we have our x version. X is equal to y squared plus 3. Yep, that's positive, so it fits on the right side. We're looking good so far. So our radius on the right is y squared plus 3. Our boundary on the left is going to be 2. So let's look at our big R. I'm going to erase this, give myself some space to work. Actually, no, I have a lot of space to work. So what's our big R and what's our little r? Our big R is y squared plus 3 minus 2. That's our big R. Because it's our right, which is our y squared plus 3, minus our 2, x is 2, whoops, because x is our axis of rotation. 2 is our axis of rotation. What's our little r? That's our boundary at x is equal to 3. That's 3 here, right? 3 and 2. So little r is 3 minus 2. Right? 3 minus 2 right here. So our big R is y squared plus 1. Our little r is 1. Now please do not do this. Don't be like, oh hey, it's going to be y squared plus 1 minus 1. This is absolutely wrong. Because in our setup, it's the integral, pi integral of r squared minus r squared. Okay, r squared minus r squared. So we have to leave these r's separate. And from 0 to 2. Okay, 0 to 2 because that's our boundary, right? From 0 to 2. Climbing up. Okay. That's it.